Any question about previous session? Today we want to continue our discussion about variational autoencoders, and hopefully we can finish them today. You remember that we start with a high-level and abstract representation, which is latent, and then claim that condition on that latent or unobserved data Z, the distribution of your data can be more easily modeled using, for example, a Gaussian distribution. In contrast to when you want to model the data distribution itself, the conditional is easier to model because you have some high-level information about what you observe. Okay, then we continue about the challenges and the solutions. Let me recap what we have seen in this slide. This slide, to some extent, summarizes several challenges we have seen. Yeah. So we see that to have a latent variable model, to have a model with a latent random vector, we need to compute the data likelihood. We need to calculate an integral like this. This integral is not tractable because the dependency of this Gaussian distribution over the latent is very complex through a neural network, one neural network that generates mean and one neural network that generates the covariance matrix. So this integral cannot be calculated tractably, and it does not have a closed form solution. So our solution to handle this challenge is to cast this integral as an expectation over the prior distribution over the latent. It means that you should take the expectation of the conditional likelihood over the samples coming from the prior latent distribution. We see that this solution, although if you are capable of calculating the expectation using Monte Carlo estimation with lots of data, but in the real world application, you want just to sample 1, 2, or 3 of Z and calculate this expectation or estimate it. So using limited number of Z, you will have a high variance in your estimation. So this solution is not a practical solution. We should replace it. The replace was the importance sampling, where we replace the sampling from the prior of latent into a Q distribution. So using the importance sampling, we see that, for example, if we select this importance sampling, if we select this distribution as the posterior for a GMM, then we don't have high variance in our estimation. Then the new problem arises that what is a good Q distribution? So we should optimize over Q distributions too. Then to solve this challenge, we introduced the concept of ELBO. The ELBO is a lower bound on the evidence or the log of this likelihood. And we see that using ELBO, the best option for this Q would be the posterior over the latent given the observed. Here we prove that the best option is the posterior. In this case, we just show that for GMM this option is good, but in the part that we talk about the solution to challenge 3, we show that the best option for the Q is the posterior over the latent given the observed data. But there was another challenge. The posterior over the latent given the observed data is not tractable because it also needs data likelihood. So you cannot select Q equal to the posterior. To solve this problem, we see that we must minimize the KL divergence between these two distributions, but one of them is not tractably calculated, so we should replace some other solution, and we see that by maximizing ELBO, we can minimize the KL divergence. Why? Because we see that the evidence, the logarithm of data likelihood equals the ELBO ELBO, the notation is phi, maybe lambda, yeah. We still use the notation lambda, we will update it. Plus what? Yeah, plus KL. KL between your Q over Z and the posterior of your model over Z given your observed data. Why maximizing ELBO with respect to Q equal minimizing KL with respect to Q to lambda? Q and lambda are interchangeable because we want to optimize Q using its parameters lambda. Why maximizing ELBO with respect to lambda is equal to minimizing KL? Because of the other side. The other side is independent of lambda. So if you maximize one of these terms with respect to lambda, you minimize the other term with respect to lambda. It means that we do not have access to this KL because we cannot calculate the posterior over latent, but we have the ELBO. If I maximize ELBO with respect to lambda, I am also minimizing the KL with respect to lambda because the summation must be independent of lambda. Clear? So we reach a solution so that we can design the distribution Q. How? First, we parameterize it using lambda. Then we maximize ELBO with respect to lambda and show that this maximization is equal to minimization of KL with respect to lambda, which is our objective in minimizing this KL. So we have this maximization too. We also want to maximize ELBO with respect to theta. Why? Why we want to maximize ELBO with respect to theta? ELBO is a lower bound to the evidence or log likelihood. Excuse me. I have no access to the evidence or log likelihood directly. So instead, if I maximize its lower bound with respect to model parameters, hopefully I am maximizing the likelihood too. So the model is going to be trained by maximizing the ELBO with respect to theta. On the other hand, we need to maximize the ELBO with respect to lambda too. Why? Because we want to tighten it, to have the best Q distribution. So we want to simultaneously maximize ELBO with respect to both theta and lambda. Yes.
Which one is easier to optimize? KL, minimizing KL or optimizing ELBO?
We cannot interchange them. The first step, you want to have a better ELBO, so you maximize with respect to lambda. You do not have a closed form solution in the general case. It's very hard. It is non-convex, very non-convex in several, with respect to both variables, But first, you want to maximize with respect to lambda so that you have a better ELBO. Then you want to maximize with respect to theta, so you will maximize the evidence. It means that each of them, but they can be interchangeably used. But in alternative maximization, you will solve the learning or training problem. So this is the. We also talk about we want to to maximize ELBO with respect to lambda for tightening, with respect to theta for learning. So we need a gradient. We need a gradient of ELBO with respect to both theta and lambda, and this is our new challenge. We want to calculate them. We see that with respect to theta, everything is can be easily calculated. The gradient is with respect to theta. The expectation is with respect to q lambda. So the expectation does not depend on your parameter you are taking the gradient with respect. So you can change the order. You have an expectation of some function, and you know that the expectation of some function can be calculated using Monte Carlo estimation. And the second term is independent of theta, so you can omit. So to estimate this gradient, you can easily use this summation. This is the gradient with respect to theta, and you can optimize your objective, which is ELBO, with respect to theta by iteratively going toward this direction, not the minus. Okay, but we have another challenge. When we want to take the gradient with respect to lambda, we have a problem here. You have a distribution, you have expectation with respect to the distribution, where the parameter of the distribution is the parameter you are taking the integral. And they cannot be changed, the order. Because if you change the order, it means that some information is going out of the gradient while it is a function of the gradient. It is the gradient variable. So here we have a challenge, and it's the challenge number 6. We see that reparameterization tree can solve this challenge. How? We start by limiting Q distribution to the normal distribution with two parameters, mu and sigma 2. You have instead of a general Q distribution, parameter Q distribution, we select the Gaussian here. So the lambda is mu and sigma 2. And we know that if I want to sample from a Gaussian with these parameters, I can sample from a standard Gaussian like this, the distribution. I sample epsilon from this distribution, and if I apply this transformation on epsilon, I have a random vector which follow the distribution of Q. Why? Because if you take the expectation and you calculate the gradient, the covariance matrix, you will see that the expectation is mu. It is very simple because linearly we can expect each term. And the covariance matrix can also be calculated as sigma to I. So it is not, there is no difference that I sample from this distribution or I sample from a normal distribution and transform and pass the resulting random vector through the transformation like this. I call this transformation G epsilon and lambda. It means that it's a transformation except in the input a sample from standard normal distribution and also the parameters of your Q distribution, both of them. So what happened? How this reparameterization can help us? Assume that I want to calculate this gradient, the gradient of this expectation. Now I replace the expectation with respect to Z coming from Q lambda with expectation over epsilon coming from a distribution which has no parameter. It is a fixed distribution. While instead of Z in this function, I use G of epsilon and lambda. What happened? Nothing changed inside the gradient. Why? Because instead of sampling from this distribution, you sample from a normal and then transform it inside your function. And everything is not changed inside the function in the expectation. Because again, G of epsilon and lambda is coming from the Q lambda distribution. We showed in the previous slide that this is coming from the what you are, there should be a line here. This comes from this Q lambda distribution. So nothing changed inside this function, so you can we can infer this equality sign here. And now The difference is that then now you can change the order, because expectation, the distribution for the expectation has no parameters, and lambda can go inside the expectation, as here, and simply you can take the gradient of this function, and then the expectation can be calculated using Monte Carlo estimation. We have an expectation of a function. I can replace it with sampling from this distribution, which is a standard normal, and then take the average of resulting functions inside the expectation. This is what Monte Carlo estimation provides. Is it clear? Reparameterization solve the problems. How? By making the distribution you are taking the expectation a normal distribution, which can change the order of the gradient and expectation. So another challenge is solved. We can take the gradient with both theta and lambda. Theta was really easy because we have no problem with changing the order, but the lambda needs some modification, which is reparameterization trick. And these are the reasons for three equalities. So now pay attention to this figure. I want to check two updates of ELBO, maximizing ELBO. What is happening? I am training a model, and I know that I should maximize the log likelihood as a function of theta over theta. I cannot calculate the likelihood itself. Instead, I maximize over theta and lambda something which is a lower bound to this likelihood, to this log likelihood, which is ELBO. This ELBO is for one point, and it has two sets of parameters. First, the model, and second, the lambda. The lambda is responsible to tighten this lower bound. The theta is responsible so that if you maximize ELBO with respect to theta, it means that you are hopefully maximizing the log likelihood also. So, assume we are at this point. We are at the point you do not have access to the blue curve. The blue curve is log likelihood, which is not accessible for you in the variational autoencoders. Instead, I have an ELBO as a function of theta, model parameters, and the Q distribution is lambda 1. So what can I do now? I have an ELBO. I maximize ELBO with respect to theta. This is an ELBO with respect to theta, and lambda is fixed. So I go to this point. Hopefully, I can recover the best the best global maximum here. It cannot be achieved in practice, but assume that I can reach this point. At this point, I have maximized the lower bound to the likelihood. What happened next? At this point, I want to tighten this lower bound. So I maximize the ELBO at the new parameter theta 2 with respect to lambda. What happened? I have a new ELBO. Why? Theta is not changed, but the lambda is changing in this step. I have a new lambda, lambda 2, and I am sure that in this point, just in this point, I mean theta 2, the new ELBO is better than the previous one. Why? Because I maximize this ELBO. What the step from the red to the next one is this one, maximize. I maximize with respect to lambda the ELBO of theta 2 and lambda. It means that lambda is the initial point. The initial point, I know that the initial point in lambda 1. I maximize the ELBO starting from lambda 1. Because I am maximizing ELBO, it means that at that point, theta 2, I am certain that the new ELBO is better lower bound to the log likelihood. You can see here. The previous one is the red, and the new one is this, let's say, magenta curve, okay? And it is a better lower bound because the distance here is lower than the distance between the red and blue curve. Why? Because I maximize elbow with respect to lambda. It is a better lower bound, where it is a lower bound at theta 2. If you change theta, everything will be changed. Because this lambda is the resulting lambda here, call it lambda star, is a function of model parameters. If you change the model, the lambda star will be changed. It is evident. Why? Because we know that maximizing elbow is intended to minimize, with respect to lambda, the KL between your Q lambda Z and P theta of Z given X. If you change theta, you are at a new point. You want to minimize the Q with another distribution. Okay? So just at point theta 2, everything will be valid. It means that the new elbow is better than the previous one in estimating or lower bounding the log likelihood. Yes?
So as you show here, I'm assuming theta 1 in case of optimizing theta.
Yes.
Theta 1 is better than theta 2 because it's like more than.
No. You know, this is the problem with variational learning. You are not sure that the likelihood is also increasing because you are maximizing a lower one.
Yes, I know. Like this is the problem here that theta 1 theoretically is better than theta 2, but since we are maximizing the elbow in respect to theta, we are choosing theta 2, which is not good in this case. So this is my question, that practically in the experiments, like how often does this happen that we are choosing theta 2 because like elbow is maximized there, but in the real case, the log loss function is basically lower?
Yeah. You know, for example, in the starting iterations where your model is not a good model, if you start to sampling even from the posterior of the model, you know, we cannot certainly talk about your question. For example, we cannot say that it is always in the starting iterations, maybe this happen more frequently, at the end iteration, no. But we know that whenever the elbow, next we will see that this Q is not trained for each data sample. We will see a technique amortization that change the gain. Okay, if the model that generating that amortized parameters will be converged, we are to some extent sure that elbow is a good lower bound to the likelihood. We will talk about it this session, yeah. But we cannot certainly talk about when this happened or when you are really maximizing the elbow. Yeah. But in practice, you will see that variational autoencoder works. So yeah, in practice, they are maximizing the likelihood to some extent. Any question? And the next step is to work on this new elbow. You consider that we do not have access to the blue curve. We just have access to these curves, the elbow curves. Now we are at the new elbow. I should maximize it. The new elbow has a new lambda parameters. I should maximize it with respect to theta. And again, I go to this point, theta 3. And this procedure will be continued and followed until you converge. And in this case, the model will be trained. You are simultaneously maximizing the maximize elbow with respect to lambda so that you have a better lower bound. Then you maximize with respect to theta, you have a better likelihood. And by your progress, you will see that this lower bound becomes better and better in terms of lambda, and then you are better estimating the log likelihood and training the model. Assume that you have access to this model posterior. When we have access to this model posterior, we have examples in the presentation that we have access to the model posterior, where in the case of GMM, you have access to the model posterior. When you are you have access to the model posterior, you can easily set Q equal to that model posterior. And in that case, when you maximize in this step, when you maximize with respect to lambda, you definitely go to the likelihood, because we know that if you have access to the model posterior and select that posterior as your sampling distribution, then likelihood and ELBO touches each other, and when they touch each other, maximizing one with a small enough step will definitely maximize another one in that neighbor. And you are always maximizing likelihood. Yes.
So the example that it shows here is just for one data point, right?
For
one data point.
Yeah, for GMM with two categories. Yeah, we talk about the GMM with two categories, and you see that everything was very simpler than this case. This is just a typical example, and in practice, you have much more complex functions. Yes.
So the orange one is ELBO for ELBO plot after first iteration. The pink one is after second iteration. So is it like after n iterations, the ELBO plots try to replicate the actual log likelihood? It's like almost similar kind of curve.
We can just say that when you maximize with respect to lambda, you have a better ELBO. ELBO in that point. The only thing that we can rely on is that when you maximize with respect to lambda, you have a better lower bound. We cannot see that how their figure match each other. In the case that you have access to the posterior, they touches each other. It means that the gradient, their value is equal because they touches each other. Yeah, just this one. Yeah, we cannot talk about, for example, their value or their maximum or minimum points. Okay, this is just a visualization of how variational learning works in the case of VAE. So the challenge number 6 was that you have you need to take this gradient with respect to lambda, and we see that the reparameterization tree can solve the problem. How? By changing from queued lambda distribution to a standard Gaussian distribution. But we have another challenge. And that challenge is that we want to maximize the log likelihood over the whole data set, not a point, not just one point. Everything that we talked about during this presentation was around 1 point x. We just maximize the likelihood of 1 point, the ELBO for 1 point. What happens if we are working with a data set? So now we want to talk about learning VAE. We want to consider the complete data set. For example, nx observation. So everything is similar, but we just add a summation. We know that the likelihood of one data sample is lower bounded by ELBO. If I want to train the model, I want to maximize this average. We know that this average is a Monte Carlo estimation to a model likelihood under data coming from true data distribution, which minimizes the KL divergence between your distribution and true data distribution. So I have several points. For each of them, I know a lower bound named ELBO, and I know that the ELBO maximized over the parameters for that data point. Pay attention to lambda I. It means that each lambda is dedicated to just one data point. The evidence for that data point is greater or equal than the maximized ELBO with respect to lambda I. If I take the summation from both sides, again greater or equal sign will be remained, and because these ELBO terms, each of these ELBO terms is a function of one of these lambda values, so I can change the order of the summation and argmax operator. Pay attention to that, because each term is, for example, for the first one is independent of all other data, I can change the order of these two operators, the summation and argmax. So I can say that what I want to calculate over the whole data set is greater or equal than this summation, the maximum of this summation. So what I need to learn the variational autoencoder models is greater than this value, because I want to maximize this summation for learning, I can instead maximize this summation over ELBO. So the learning will become in this procedure. First, I maximize the ELBO for each of the data points, make each data point tighten, the ELBO for each data point tighten, and then maximize the whole summation over all ELBOs. And in this case, I can train the model. Any question? Just an extension from one data point to the whole data set. It is very similar to what we have before. Okay. So one point, why I select one Q distribution for each data point. Assume that I have x1. Here, I assume that I have lambda 1. It means that for ELBO, at this point, I use Q lambda 1 over Z. When I go to another data point, for example, x2, I use lambda 2, which means that the sampling is coming from this distribution. Why? Pay attention to these two curves, two GMM samples. If my data point is here and here, can I share one posterior for both of them? It is clear that sharing a posterior for both of them will not work, because the posterior here, these three groups have higher probability, but here just this group has high probability. You know that because the covariance for this is not spread. This is the highest probability, and all other groups are 0. So if I want to use one distribution Q lambda Z, it means that I should select something for lambda that works for both of these two cases. And you cannot select something because they are completely non-overlapping. Is it clear why you should select one Q distribution for each data sample? Okay. And this is the stochastic variational inference learning. Nothing more than maximizing the ELBO over the whole data set. What happened? You have a data set, you have a set of Q distributions with their parameters, and you start training. This is the procedure you train a variational autoencoder. Based on this idea, you can train a variational autoencoder. You start by tightening the ELBO. This for loop is for tightening the ELBO for all data points. For each of the data points, you select one sample from the data set here because it is stochastic. One sample from the data set, and then you have k iterations for that data sample to optimize its parameters. Then you have a tighten ELBO just for xi. What happened next? You maximize the ELBO with respect to the model parameters. It means that the model becomes a better model for that data point. and then continue this procedure by selecting other samples from the dataset. So it means that assume that again you select xi. You cannot use the lambda I again, because the lambda I was for the previous model that was selected in the iteration. Pay attention. Assume I have a xi sample. It's enter the SVI, the stochastic variational learning, SVL. Excuse me. It enters the algorithms. What happened? You train a better Q distribution for that data sample and update theta. Then, through the iterations, this theta will change. Assume that I call it theta 1. Then, using other samples, xj, j other than I update the model using the same procedure. So at the end, I have for example, theta k. What happened next? Again, xi is selected to update theta k. In this case, you cannot again use lambda I. Why? Because lambda I is optimum for the model here. The model here, assume it has theta 0. In this case, the model parameters is theta k. So this is totally a new model. So you should you should find another optimum lambda I, and then continue the procedure. Just remember that these lambda I are also evolving through the iterations. Any questions?
So, can't you do it in parallel process? Because
yes, you can take a batch of data set, and then but this iteration is for each of the data samples. You should have a different maximization of ELBO for that samples, because lambda I is dedicated to one sample, nothing more. Yes.
Pseudocode. What is the 4J equal what? Where's J? That's supposed to be I.
Oh, it's a problem maybe. For J1 to D.
Not be I, because I don't see the for loop that's iterating over the data set.
Yeah. No. You know, it is the number of iterations for updates. You know, you cannot see it anywhere. Assume that my budget is that I can update the parameters of the model for D times. Okay. I start with the first update, select one sample from the dataset, name it xi, go through this loop to optimize its parameters, sampling parameters, and then update the model again using that xi and lambda I, and then update j. It means that I have a budget of D update for the model parameters. Is it clear? Okay. So the challenge number 7 was also solved. We can now maximize the ELBO overall model, dataset samples. But this formulation may cause another challenge. What is that challenge? Pay attention to the formulation. Something is not aligned with other models you may see during your previous courses. Here, by increasing the dataset size, the number of your model parameters will be increased. Assume that I'm using MNIST. I have, for example, 60,000 lambda I. I go to ImageNet. I have much more parameters for the model. You know, the model parameters will be changed. And it is not favorable. Why? Because it cannot be scaled to a large data set. Is it clear why we have challenge? Okay. The new challenge is that the number of optimization problem and the parameters for the optimization problem will be increased by increasing n, the uppercase n. And in other words, each training sample adds one lambda vector to the optimization problem, to the problem. The problem will be, when you have a larger problem. So The solution is a technique amortization, and we will talk about the technique now. So, we know that using SVI, I can solve this problem, stochastic variational inference. I can learn a model using ELBO, okay? But amortization is a technique so that the number of these lambda will not increase if the n value is increased. But how? In the previous session, we see that each data point has its own lambda parameters. Now, instead of this procedure, I design a model, a neural network. These neural networks, if input x, the neural network will output the optimum, hopefully, the optimum parameter for sampling for x. What happened here? Here, instead of considering a set of lambda, one lambda for each data point, we just have a function. This function, if you input x to the function, it generates the parameters for you. It means that all the data samples share an architecture to generate their optimum sampling parameters. Does it make sense how it can solve the problem? Instead of each data sample has its own parameters, you form a model, and this model, when you input x into it, generate the optimum parameters. And now the parameters are just the parameters of this black box, this neural network, this model. So if you increase n, the number of parameters for this model will not be changed. So everything would be scalable with respect to the dataset size. Does it make sense how it can solve the problem? Yes.
So here, lambda is still function, the mean and the variance is still the function of x.
Exactly. Yes. Yes.
So I not understand it correctly. So lambda is still the function of the input.
Yes.
So how is it the same for all the inputs?
But in this case, you will not have a lambda for each x. You just have a model with parameters phi, and that model can generate lambda for each of x. You know, it means that, as you said, if x changes, lambda will be changed. But the parameters of the optimization are just this phi. You know, you have a black box. Previously, each x has its own lambda. x1, lambda 1, x2, lambda 2, till the end. Now, you just have a parameter phi, and when you input x into this f function automatically select or generate an optimum lambda for you. You do not have a lambda for hx. You are not free in that way. You are constrained to this function. This function generates the lambda for you. So you are not optimizing over lambda anymore. You optimize over phi.
So what is the difference on optimizing over lambda? Now we are optimizing on like phi.
Yeah. Over this phi variable, it means that, assume I have n equals 6,000. In the above scenario, I have again 60,000 lambda. But in this scenario, it just depends on how many parameters does this model have. For example, assume that it has 1,000 parameters. If I scale the number of dataset samples from 60,000 to 6 million, okay, what happened above? I have 6 million lambda. What happened here? I again have 1,000 parameters. Nothing changed. Yeah, and it makes everything scalable. Yes.
And how well is this estimations for lambdas? It doesn't produce like multiple lambda average data points.
There is a dependency on the data point again here. there is dependency over data points. So the things we talk about here will not happen. Because x is changed, the parameters will be changed for these 2 points. You understand? There is dependency on the data point here. It means that each data has its own sampling distribution. But there is a limitation in comparison to the previous approach. I agree with that. But when you are in the limited data set size, maybe this limitation will help you. And you can see that this will generally help you in training the model. And there is another more important point with this, let's say, amortization. You know what? Assume that you train your model, okay? And I give you the new data samples. What happened now? If we are working on 1 lambda for each data sample, you should optimize the parameters with respect to that data sample. But now you have a trained model. You input the new data sample into the model, and you have the posterior over an approximation over the posterior. Something maybe you asked in the previous session that in the inference time for the general model, assume that I am in the previous approach. Each x has its own lambda. Now I have a trained model, and I give you a data point x new, and ask you for the ELBO for this new data. If I am using the previous approach, I first should find a lambda new for this data point, and this needs optimization. Why? Because each data point has its own lambda. What happened now? Assume that in parallel to the model, I train f. It means that I have both theta star and phi star. Now what happened? It is not needed to optimize. I just input x new into our model f of phi star, and at the output I have lambda star for the new data sample.
And how close are the lambda stars and the lambda?
It definitely it's better to have an optimization, but when you have a limited data samples, this amortization can also help you in generating, sampling a better lambda, from a better distribution. It means that if you have lots of data, maybe optimizing this lots of data and resources, optimizing the procedure maybe works better. But you are in the limited resource, in the limited data set, and in the limited scenario, this works better.
Okay.
Yeah, in practice. Yeah. Yes.
So in the ideal case, this amortized structure is overfitting over the trained data, right?
In the first scenario.
So in the first scenario, we have the lambda for every parameter that's completely ideal case. And then we design this structure to make it maybe more practical and practical. Yeah. So, but if this model is able to somehow overfit over the trained data, that could be somehow the same as the first model, right?
Here, if this one overfits, the situation will be much worse than here. Why? Because in this case, you train the model, and then for each new data sample, you generate its own parameters. But here, you say that it is overfitted to the training data. What happened? The new data is coming, and the new data is not from the training data, for example, distribution. So a very, let's say, garbage output you have here, and the sampling is not from a suitable distribution. But here, because you optimize for that samples, maybe you have a better situation. But in this case, you should monitor the overfitting, and you can monitor it using ELBO over the training validation sets. Yes. Yes.
So how do we train, like, what is the loss function here when we feed forward?
Yeah.
It's like we get a new and a variance. Yeah. So what is the loss? How is the loss computed? What is like the
Previously, you know how to backpropagate the loss to these lambda parameters. It just have another backpropagation through this model. Here, lambda are not being updated. You know, you can backpropagate the loss into lambda. Okay, just continue the backpropagation through this network, and then because lambda is not a parameters anymore. Okay. You just backpropagate the data through this model and optimize the phi variable.
No, I mean, like, we have a mu and a variance. So what is a good mu and variance that we are comparing to it to get the loss and then backpropagate?
About the complete loss we will talk. Maybe it is not clear yet. Yeah, I will talk about it, hopefully today. Okay, so amortized inference, you have a shared structure, and that shared structure or architecture generate an approximation for the posterior over Z given X. Pay attention to this notation change. Previously, I mentioned it as Q lambda. Now I represent it as Q phi of Z given X. What happened? Nothing changed. Just the parameters are not lambda anymore. It is phi, the parameters of the amortized model. And also I add this X here. Why? Previously for the Q lambda, I do not have X. Why? Because in the previous cases I was just working in one data sample. But here I know that the amortized architecture need X as input, and at the output generate the distribution. So I use this notation. Q phi of Z given X. And these two parameters, mu and sigma 2 phi, are generated using your amortized network. Okay, so another challenge is solved. How? By amortization. Amortization will share a network to generate the parameters for all data samples, and it will be helpful during your inference that you do not need the optimization. Any question about amortization? Okay, so the notation update. Previously, we talked about ELBO of x, theta, and lambda. Now we have ELBO of x, theta, and phi, and we know that ELBO previously was the expectation over z coming from the q of log of the joint over the q lambda. Here I replaced q phi of z given x. This is just a notation update, and pay attention to this phi, which replaced lambda previously. And this is also the other form of the objective. So I can update the stochastic variational inference by updating the way that we update phi instead of lambda previously. If you remember here, we have a loop. We have a loop to optimize the parameters for the data sample. Here we just have one update for the phi given the data sample xi. So first, I update the parameters of my amortization network such that the output parameters are better parameter for sampling to generate the posterior over xi. Then I update the model parameter. Now, to approach a better view to the loss function, I want to revisit the objective function of ELBO. Yes. Any question? We now, to some extent, can calculate the gradients. We see that how to calculate the gradients. If you have the gradients, you can update the parameters, you can maximize the ELBO, you can train the model. Everything is finished now, but we want to change the loss function of the ELBO formulation so that we have a better view to the optimization problem. And you will see that how you can definitely update each of the model parameters. I have ELBO. ELBO is the expectation over the Z coming from this, we call it approximate posterior, because it is an approximate posterior to the true model posterior, okay? The expectation over the approximate posterior over the latent of this function. This is the definition of ELBO. If I add and subtract the log of, I have a problem here, you know. This is also p theta of z. They are exactly the same. I subtract and add one term to this function. So nothing will be changed. If I add and subtract log of p theta z to this function, I have the combination of these two terms is the log of p theta of x given zy, because it is the logarithm, the subtraction of these two logarithm is the logarithm of the ratio. So it is the logarithm of p theta of x and z over the p theta of z, which is the p theta of x given z. One point. And the other term is the minus the logarithm of pz, the logarithm of pz minus the logarithm of the approximate posterior. And again, I can make it the ratio of the ratio of the distributions. And now pay attention to what happened next. I have the expectation over the approximate posterior of this term. Again, I write it here without any change. But the next one is very interesting. The expectation over the approximate posterior of this ratio. What is it? KL divergence between the numerator and denominator. Why? Because we know that the KL divergence is the expectation with respect to the first distribution of the ratio of first to the second. So I have a KL divergence here. The objective function is changed. It means that when you maximize ELBO, in other words, you are maximizing this term. And it is more intuitive than the original ELBO, the new one. Let's think what is the new objective function.
Can you go back?
Yes.
Why the denominator is log of?
Oh, it's my problem. That's the p theta of z.
Okay.
Yeah.
Thank you.
Thank you very much. Pay attention that we have an extra log here. Okay. So let's think of this formulation. What happened? We have an encoder. Why we call it encoder? Because from the observed data, it generates a distribution over latent. From observed, you go to the space of latent. You do not definitely have the latent. You have a distribution over the latent. So it's encode the data into a new word. And the new word is where you have latent, your latents are valid. Is clear? So we call it the encoder. What happened next? What is here? What happened next? In the next, I want to calculate this expectation with respect to z coming from the approximate posterior. So I know that any expectation can be calculated using Monte Carlo estimation by sampling from this distribution. I replace the sampling with just one sample. What happened? I sample from the approximate posterior and call it lowercase z. This is the one latent. This is not the random anymore. This is one latent. But this latent is related to your input. Your input enter the amortized approximate inference network. That network generates a distribution over the latent. This distribution is related to xi. Anything is for xi. Then you sample from that to calculate this expectation. we can calculate the expectation with just one sample. I want to calculate this expectation with just one sample. So I sample from the approximate posterior and name it Z. This is a latent value, not a random. Then I input this Z into the let's call it encoder or decoder. This is decoder, but why decoder? This function p theta of x given Z transfer you from one data point in the latent space into a distribution in an observed space. So you are going from the latent into observed. So it is to some extent decoding what you have in your latent space. So we call it decoder. This is my mistake that I write it encode. This is decoder. Okay. Again, this Z input here, and I pass it through the decoder. What happened? Excuse me. Here. I sample from this distribution, pass it through this function. I want to maximize the result. Why? Because I want to maximize this whole term. This is the ELBO. So everything will be clear now. I have a distribution over the posterior. I have a distribution over the observed data. Excuse me. So now I want to maximize the first term. Just focus on the first term of ELBO. I am maximizing this term. What happened? I input X into the amortized inference network. That network generates Z. That Z is suitable Z to calculate this expectation. Why? Because it is a Z coming from the posterior, approximate posterior. Then I input that Z into the decoder function and generate something. If the generated samples is near my input sample, it means that it gives high probability to your input data. So again, pay attention. I input Xi into a model, and that model first generate a distribution over Z given Xi, and then I sample from the distribution as call it Z. Okay? In the next step, I input this Z. This Z is the Z coming from Xi. They are related to each other. I input this Z into p theta of x given Z. This is a random variable now. This is a value. And then I generate a distribution over X. Okay? When the expectation of this function for Z coming from approximate posterior, this distribution, to maximize this expectation, this distribution should be maximized in which point? In the point which start the procedure. It means that encoding and decoding, you know. I encode something into a posterior distribution, then I sample from it. Why? Because I want to calculate this expectation. I sample from it and input to the function here. This function should be maximized at the point you start the procedure with. In that case, you have the best encoding and decoding procedure. And your log marginal likelihood, your log conditional likelihood will be maximized. I don't know whether you get the point why the log conditional likelihood should be maximized at xi here or not. Because xi start the procedure, and xi is coded into z, and you are sampling from the posterior of that xi, the approximate posterior of that xi. So the resulting xi at the decoder, the resulting distribution over x at the decoder should be maximized as at your xi input. This is the intuition of the first term. It is the intuition is something called reconstruction. You know, you have input xi into your approximate posterior and then sample from it and call it z. If you enter the z into a good decoder should output with high probability your input xi, because zi is coming from the posterior of that xi. So we want to maximize this expectation. It is a reconstruction term. You reconstruct the sample you input to the amortized inference network. Does it make sense? Okay. So what happens in practice? You select an xi, generate the approximate posterior over the latent given xi. It means that this q phi, sample from that, generate the model posterior x given z, and then a good model is one where this value is maximized because xi was the input to the encoder part. Now I have a sample. Assume that the decoder, assume that for the decoder part, we again consider, remember the first slides about the variational autoencoder, we see that given the input, given the latent, you generate a distribution over the x. This model at the output gives you two parameters. One of them is the mean, and the other one is the variance. And when you input a z into the decoder, it generates two parameters for you, and you want to maximize the log of this normal distribution at point xi with these parameters. So you have a function. If you write down the normal distribution formulation and take the logarithm, you have an exponent, you have a logarithm, you have these two terms. In other words, by maximizing this log, you are maximizing these terms, or again, minimizing the negative sign. The negative sign, pay attention. The first, I just write down the second one. The second one is xi minus. You are minimizing this term over the model parameters. What happened here? It means that the decoder generates a mean and the covariance for the output. The mean should be near to your input. This is a reconstruction. You are reconstructing the input data xi using your decoder part. Maximizing the log likelihood here, maximizing the log conditional likelihood here is equivalent to minimizing the distance of x with this mu theta vector. The optimization with respect to theta is straightforward. But again, we know that in this function, we have dependency over phi. How? We do not see any phi here. Well, how is the dependency over phi in this term? How is mu theta generated? The dependency is very complex, but pay attention. How is mu theta generated? It is the output of this model. This model is triggered by a z. Where is z coming from? Z is coming from this distribution. and here you have phi. It means that the z that you sample from is a function of phi. So what you have here, or what you have here, is a function of phi. And you should maximize with respect to phi too, but we know that for maximization with respect to phi, we need reparameterization trick. We cannot maximize it because you have gradient of expectation and they cannot be changed without using the reparameterization trick. This is the variational autoencoder with reparameterization trick. What happened? I input X into the amortized network. The network generates to a mean and a variance. Then instead of sampling from this mean and variance, I sample from a standard Gaussian, generate epsilon, times the epsilon is times with this covariance or with the standard deviation. It is not correct. With the standard deviation, and then the mean is added to the epsilon times sigma, and you generate z. Then you input z into the decoder part. The decoder part generates a mean and again a variance, and you have this normal distribution over the x. And what happened next? Then you write down this term, this expectation. This expectation is a function of both phi and theta, and you optimize with respect to both of them. And in this figure, you can easily see the backpropagation procedure. Can you understand how we optimize with respect to the phi? You know, at the end, you should minimize the distance between theta, mu theta and xi. This error is start backpropagating through this network and z. Then it comes here, and as you can see, you do not have anything with the sampler because you use reparameterization trick. This error is backpropagated from this path to the encoder, and from this path also to the encoder. And then you optimize the parameters of the encoder. I think the procedure for optimization is clear here, yes?
And so the goal of doing this is just like in the end, we're taking the encoders and then use that encoder to generate the lambdas, right?
The encoder is used just to generate the lambdas, yeah.
Yeah, and then this is like way too like training.
Yeah, this is the final training procedure for variational autoencoder. The practical method to update the variational autoencoder is exactly this graph, to some extent graph. It means that you start with, everything is clear I think now. You start with this loss, this is your loss. This is the loss from first step. The second step we do not talk about. We talk about it next. This is your loss. You start backpropagating this loss with respect to both parameters of the model here and the parameters of the amortized encoder. And again, you can see that any of the libraries like PyTorch, TensorFlow can calculate it for you in this graph. Okay? And we see that how reparameterization works here. If you do not use reparameterization, you should backpropagate through a sampler, which is not possible. In the standard, you have one direction from here, and these two are omitted. So you should backpropagate through a sampler, which is not possible. We do not know how to backpropagate error through a sampler. Yes?
Why do you ignore the first step, the d over 2 log of 2 pi?
That decreases uncertainty over that point, the variance over on. We are interested in to have lower uncertainty over that point. The mu theta, the mu theta is best collapse on the xi. This is the best option. This is to some extent some uncertainty over that point, how you are uncertain about your choice.
So you don't care to optimize that?
Yeah, you want to minimize the uncertainty too, yeah. But you cannot make it zero.
Yes.
Yeah.
So in the backpropagation of the decoder, you are basically minimizing the second term, this xi minus mu.
No, both of them are backpropagated. This is the last, and both of them are backpropagated through the whole network. Yes. Okay, I think our time is also over. Thank you very much.